Okay, let's get started. So I sent an email out yesterday. I want to just, if you go to exam prep, there's now an exam 2 folder. Our exam is a week from yesterday. It's next Thursday. So in the exam 2 folder, you've got the same kind of outline that you had for the first exam. Concepts and skills, that's a comprehensive list. There's nothing on the exam that isn't referenced somewhere in that list, okay? And then there's the WebWork review problems. We're going to go there in a second. And then this is actually the quiz archive from last semester. So those are all great practice problems too. I just didn't use the same quizzes. We've had less quizzes, so those are all very great quizzes to help you study. Nothing changed in the material from last semester to this semester. So you can take a look at those. When you click on this, it'll take you to WebWork. You're going to click on Ashbrook under 170. You may have to sign in to your ASU Write ID, or sign into the system. And then you'll see that exam 2 are now up. Okay, it's 60 problems. Okay, they're all very, very good practice for this exam. So I want to make sure I got them up quick, give you enough time to work on them little by little. If you start on Tuesday or Wednesday, chances are you're going to get overwhelmed. But if you can break it up into, groups of problems and maybe try to do 10 a day from now until then, that will get you on schedule to finish it all. And so it's a great way to study. I've picked these personally based on what the exam is like and what we covered. But then also, depending on how many you get correct, I'll give you some bonus on the exam. Yes, sir?
Will there be hints on it? Or?
No, I don't think there's any hints. But you can, if you go to a problem, so first know that some of the problems you get 5 attempts for the extra credit, and some you get 3. After your attempts are up, you can still work on the problem as much as you want to practice it. But if you're having difficulty, you can hit this email instructor button at the bottom of the problem that you're working on. That will give me a direct link to your problem. Everyone gets different problems. So it'll give me a link to your problem. It'll let me see your past answers. Gives me lots of helpful information to help you. So if you hit email instructor, send me a specific message. Don't just say, I'm having difficulty on this problem. You need to be specific. I did this and this and this, or this is the way I understood it. Can you help me? Or tell me where you're running into difficulty specifically. And then when you send that email, I'll get your message plus a link to that problem. So that's where you can get a hint. Again, keep track of your attempts. If you're really going for the extra credit, some of them you get 5 total attempts, some you only get 3. And then the time where it's over for trying to get extra credit will be Wednesday night at midnight. And so if you go back to the homework sets, you'll see it's now open. It's due the 31st at midnight. Now after that, you can definitely still work on it and practice, and then all the answers will be there too. So you can keep going back and you'll get to see all the answers of the ones you didn't. If you get it right, you'll know what the answer is because it'll tell you. But if you got it wrong, then any of the answers to the ones you got wrong will be available after the due date, which is Wednesday night before the exam. Questions about WebWork? Or questions about getting ready for the exam? Okay? You got to practice. You can't just hold the book open and flip pages and kind of be like, oh yeah, I remember that. That's not studying, okay? You got to practice. You got to practice with the ideas, and you practice with the ideas by getting practice problems in front of you. And just ask yourself lots of questions about the meanings. Always meanings of the numbers, meanings of the symbols, meanings of the expressions. Anything about studying for the exam? Okay, so we basically have 2 more days to finish up Module 5. It's a much shorter module, so we're going to do that. And then Wednesday, we'll start new stuff, but it'll have enough, it's based on enough of the stuff we're doing now that it's still kind of worthwhile for the exam, but it's not specifically on the exam Wednesday stuff, but still uses a lot of the same things that we'll be building up now. All right, so what am I wanting to do here? I'm going to start on this one. Good distance. I got it. Okay, here are some of the functions we talked about so far. Does the first one look familiar? V equals R of x. Remember what that one was? 11 minus 2x, 8.5 minus 2x times x. That was the box from a 11 by 8.5 piece of paper, right? So that was a function because it was input and output. What was the input of that function? Yeah, it was the cutout length, right? X was the cutout length. And then we could build this formula that if we pick a particular cutout length, the output of that function would give us what? The volume of the box after you cut those squares out and folded it up. Okay? So we worked on that. So what kind of function, just in general, what kind of function is this one? What kind of covariation does it model? What kind of covariation does that model? 3x minus 4. Linear, which was what kind of covariation? Not proportional. Because of the minus 4. It's not proportional, but it is constant rate of change. Constant rate of change. Okay? Here is some kind of, looks like some kind of circle area function. Constant rate of change on that one? Why not? It's not exponential. Exponential would be if the x is in the exponent, but it's a higher power of x than 1, right? So this is not constant rate of change. What kind of function is that right there? That's our exponential function, right? Exponential function right there. Okay, so these are also examples of functions. So we want to focus on ones that are of this type, like our not coming on. I turned it off here. I did turn it off, that's why. So the next type of function we're going to talk about, or next types of covariation, is polynomial functions. So the question is, which of these are polynomials? Which of these are polynomials? If maybe you remember from previous advanced algebra class, is this a polynomial? Yeah, it sure is. What about this one? Yes, it's polynomial. So we're going to see why in a second. Yes? What about this one? Yep. How about this? Is it a polynomial? No, it's exponential. Okay, exponential are not polynomials. This one also, this is a log function, so it's not polynomial. So all of these are polynomials. So the question is why? So what is it about these that make them this category of functions polynomial? What do they all have in common? Okay, well, let's take a look. So here's polynomials can be written in this form. Okay? This is called our standard form of a polynomial. Okay? So the pattern here is that we have terms. We have a sum of terms. Each term has x to some non-negative integer. So n is a non-negative integer called the degree. And so all of these powers are then, that's 1, and this is like x to the 0. All of the powers are non-negative integers of x. So we have a sum of terms. Each one has x to some non-negative integer. That's a polynomial. Okay, and then each of those terms can have these are called the coefficients. So the a values are the coefficients of those x terms. Okay, so we've got the coefficients of the terms. Each one of these things added together is a term. And so this is a special term right here. This is what's called the leading term. The leading term is the term that has the highest power of x. And that highest power of x is called the degree. That's the degree of the polynomial. Okay, so the leading term, again, it's the one that has the highest power of x. That power of x is the degree of the polynomial. The coefficients are the real numbers that are multiplied by those x terms, or by those x expressions. Okay, over here, this is a special term where there is no x, or it's x to the 0. That's just called the constant term. So questions on the nuts and bolts? So we need the language. So when we've got a particular polynomial, we can I can say leading term, and you know what I mean. I can talk about degree, and you know what I mean. Can I erase? Here we go. Okay, so here was our box problem. So notice that, is this a polynomial? Is this a polynomial right here? 11 minus 2x times 8.5 minus 2x times x? Does it look like what we just said? It does look like what we just said? No, what we just said was a sum of many terms. Each one has an x to the something. So it doesn't look like what we just had, but is it what we just had? Yeah, it's just we need to change the form of it. So we can multiply this out. Okay? What is 11 times 8.5? 88 plus 5.5. 93.5? Check my work. 93.5 times x. And this will be 17 and 22. Is that 39? Plus 39. That'll be x squared. And then this will be plus 4x cubed. All right, make sure I did that right. So I got minus 2x times x. That's our 4x cubed. And then I had 17x and 22x, 39.
Should be negative, not addition.
You
said plus 30.
Well, it'll be a negative and a negative, right?
Yeah.
Negative times negative is positive.
That's 4x cubed. But when you go
Is one of them a minus?
11 times
negative 2 is
2x.
negative
And then
Oh, right. Thank you.
It's negative.
This should be a total of minus 39x squared. Okay, so now it looks like what we said in the last slide, see? So there are two forms. There's standard form, and then there's factored form. And they both have their advantages. So let's talk about that. So let's just review on standard form. What is the degree of this polynomial? They're saying 3. Agreed? Yeah, you look for the highest power of x. Degree is 3. What is the constant term? What's the constant term?
The constant term.
What's the constant term of this polynomial?
Zero.
There is none, so it would be plus 0. If we wanted to put a constant term on here, we'd say plus 0. Okay? So the constant term is 0. What is the leading term?
4x cubed.
4x cubed. It's the term that has the highest power of x, where the degree comes from. Okay? So here's our leading term. Our degree is 3. The constant term is 0. What's the coefficient of the x squared term? What's the coefficient of the x squared term? Negative 39. It's the one I blew, right? It's the one I screwed up. Negative 39. The coefficient of the x term is 93.5. Okay, so that's standard form.
So the one in front of that, what we started with is factored form.
That's right.
Is that correct?
And we're going to talk about that right now. So this is standard form. Okay, and this is called factored form. What is standard form helpful for? So, let's see. It's actually helpful for a couple things. One of which is the Y-intercept.
It's plus 0.
Yeah, so we're on a graph. What's true about the Y-intercept of a graph? What is true at the Y-intercept? We know something's true.
X is 0.
X is 0. So to get the Y-intercept, we would plug x equals 0 into the function. And what will it always spit out? If x is 0, then all the terms with x's will go away, and you'll be left with what? Whatever your constant term is. So your constant term tells you what the Y-intercept is, because by putting in x equals 0, all these other things go away, right? Okay, so this is the Y-intercept is 0, comma b, and so the value of b is whatever your constant term is. So in this particular one, this particular graph goes through the point 0, 0. It doesn't have a non-zero Y-intercept like I'm showing in that graph. That was just general. Okay, the other thing has to do with, we'll do it on Monday. We won't do it yet today, or maybe at the end of class today. But the other part that the standard form really helps with is looking at this leading term. Helps us with one particular aspect of the graph. But before we get to that, I want to talk about factored form. So factored form is this over this. These are called, each one of these is called a factor. Yep, each individual thing that's multiplied together is a factor. Okay, the factored form is very helpful with what's called the zeros or the roots of the function. Okay, so I'm going to be a broken record today and Monday and Wednesday. Zeros are roots, are values of the function, values of x that make the function 0. Values of x that make the function 0. Okay? So zeros are the actual ordered pairs. So maybe a comma 0. Then the corresponding root would just be the x value. Okay? So a. So why does the factored form help us to find the zeros more easily than the standard form? So we're looking for values of x that make the function equal to 0. So why is it easier with factored form over standard form? Okay? Right. So if I were to put, we're saying where's the function equal to 0? So how can you see where the function is equal to 0 on here? What will you do?
Solve for x.
Yeah, any one of these could be 0 and we'd make it 0. So we can just look at the 11 minus 2x. If we have the x value that makes that 0, it doesn't matter what these are, we're going to get 0. So let's solve for all the roots of this function. Go. So what are all the roots of the v function?
So the root is
The 0 is the ordered pair. And the root is just the x value. So they're almost the same. So the 11 minus 2x gives us a root of x equals 5.5. Okay? The 8.5 minus 2x. We solve that for equal to 0. 4.25. Any other roots? 0. Only because we have a factor of x. If this was just a number like 4, it was 4 times these two, then x doesn't make it 0, right? The reason that there's a 0 is because if you plug 0 in for x here, you get 0. So there are 3 roots, or 3 zeros of this polynomial. And so what does that mean for the graph? What do roots or polynomials mean for the graph?
Goes through when x is 0, it goes through those groups.
When x is 0?
Or y is 0, x goes through those sets of groups.
So what are we looking at in terms of the polynomial? These are telling us, or showing us what about the graph?
points on the x-axis.
X-intercepts, right? So what x values will be 0, will give a y value of 0. So they're x-intercepts. So go ahead and start a graph and plot these points. 0, 4.25, and 5.5. A written graph, draw a graph. Draw a graph and just plot the points 0, 4.25, and 5.5. Oh, there it was. That did it for me. Okay, so notice that this is the graph of that function. Notice where we got our x-intercepts. 0, 4.25, 5.5. Okay, now this is kind of practice from last time. So it's over what inputs are the outputs of the function increasing? So when is this function, for what values of x does this function increase? You want from 0 to where? Okay, so you're seeing somewhere around in here? Yep. So whatever, there's some value here. So you could use your graphing calculator and get the maximum point. The maximum point will be where that, so from 0, less than x, less than around 1.6. Okay, approximately. Anywhere else where it's increasing?
5 to
Somewhere around 5 to infinity. So x greater than, maybe it's 4.9. These are I'm just approximating from the picture. So y, as x increases, y values are increasing between 0 and 1.5, and then also after the low point, which is around 4.9. Decreasing then, from where to where? X equals 1.6 to about 4.9, decreasing. That's this part of the graph here.
So you write that as 1.6.
Yep.
X.
You can get better approximations on if you graph it on your graphing calculator and use the max and min. The max, this local max here, and this local min are those dividing points, those break points of changing from increasing to decreasing, and then from decreasing back to increasing.
You were actually spot on for the increasing.
What's that?
1.6.
Is it?
Yeah.
The other one's probably like 4.95 or something.
0.91.
Okay, he's telling me 1.6 is right, and then this is more like 4.91. Okay, thank you. Okay, concavity. So we talked about concavity last time. From 0 to 1.6, what's the concavity? Concave up or concave down? From 0 to 1.6. Is it curved up or is it curved down? Down. And what did we say that meant for changes in y? That means the changes are
Decreasing.
decreasing. Changes are decreasing. They're decreasing because they're getting less positive, the changes, right? So if I choose a little square to be my x change, do you see that every time I go over to the right one square, the corresponding change in y is less than before. Changes are decreasing. These lengths right here, for the same change in x, are decreasing. So that's why the shape is concave down. What about after 1.6? What do we know? Still concave down. Because the changes are doing what? So here, are the changes increasing or decreasing? Changes are increasing or decreasing? This is what I tried to warn you about. Okay, the changes are negative because the y values are decreasing. So the changes are negative. Are they becoming more negative or less negative? More negative. More negative change each time. And if numbers become more negative, are they going up or down? Down. Changes are decreasing because they're becoming more negative. Yes?
I put like it's decreasing at an increasing rate. Is that acceptable?
No, this would be decreasing at a decreasing rate because the rate's becoming more negative.
Yeah, the negative is increasing.
But this,
But it's decreasing at an increasing rate. That's what the people in the math series that are going to say and teach you that.
then they're incorrect. I'm glad you asked. I'm really glad you asked. Because if the rates of change are doing this, if the rates of change are, say, -1, -2, -5, -9, -14, are those rates increasing or decreasing? They're becoming more negative. But we need to be consistent on what decreasing means. Decreasing always means x values are getting less, whether it's negative or positive. Okay? So these are decreasing rates or decreasing changes because they're getting more negative. The key is more negative.
No, why is it decreasing? Because the values are getting higher.
No, yeah, y is increasing, yes. But the changes in y, these are the changes in y. You see those changes? What are they doing? Those changes are getting smaller. Do you see? So they're getting less positive here, and then they turn negative, and they're getting more negative there. So you're always decreasing. Less positive, more negative. Decreasing, decreasing, decreasing. So this function is decreasing at a decreasing rate because they're getting the changes are getting more negative.
And it's going back to 0. So it's the y value is decreasing because it's heading back to 0. Correct?
That's right. Y is decreasing, and the rate is also decreasing, getting more negative.
So the first half of that, would that be
Increasing at a decreasing rate. Increasing at a decreasing rate. This is decreasing at a decreasing rate. See, we got to have consistency on what decreasing means. We can't have decreasing mean going towards 0. That's inconsistent. That's what feels natural. But we got to have decreasing always mean like going to the left on the number line, whether you're positive or negative. That's because we want decreasing to always mean concave down. We want changes decreasing to always mean concave down. Because if you say the changes are increasing here, well, but it's concave down, so you can't make that association. So we want concave down to always mean that changes are decreasing. Okay, what about here? So right about here we have what's called an inflection point because the concavity changes. And now what happens to the changes? So through here, are the changes increasing or decreasing? So we got to start with, are the changes negative or positive? Are the changes negative or positive changes of y? They're negative changes of y. Are they becoming more negative or less negative? Less negative. So the changes are increasing. So this is decreasing at an increasing rate because the changes are becoming less negative. Less negative means increase. So the rate of change is increasing or changes are increasing, which means concave up. Concave up means the changes are increasing. It's tricky. You got to practice it over and over again. This is easy. What happens to y? Y is increasing. What about the changes in y? Increasing, right? Every change is bigger than the last one. So changes are increasing. Y is increasing and the changes are increasing. Since the changes are increasing, we're still concave up. If we don't get that straight, then concave down and concave up, they won't be consistent. It'll mix it up. Okay, any questions on that? Yes, inflection point. We said it was right about here, where the concavity changes, right? Right about there.
So to make that more easy to see, like I said, like an imaginary line, I think above that, that's how we would know if it was increasing and increasing. Like if you draw like an imaginary line through that point and then that reflection, then we can more easily tell between, because it was hard to see in that one line that it was decreasing at a decreasing rate and then decreasing at an increasing rate, but if there was like that line, like if you created an
Are you talking about here?
yeah.
That's like the inflection point. So right here where the concavity changes, here it's cupped down and then it's cupped up. That breaking point is called the inflection point where the concavity changes. Okay? So when it's cupped down, the changes are becoming more negative. They're larger negatives, so that's decreasing. Decreasing changes. When it's cupped up and heading down, the changes are becoming less negative, or more, which would be increasing. Okay. So let's look at another example here. Polynomial. So going back to, so the reason that we're kind of, polynomials are these smooth, kind of hilly curves. So they lend themselves to this type of conversation, as with changing, the rates continually changing. So is the rate increasing or decreasing? That's why we did those bottle problems right before the polynomials. Okay, so we said that factored form, we got factored form and standard form, right? Let me just open up a window here. So what was our factored form of the v function?
11 minus 2x times 8 minus 2x.
And then our standard form?
93 x minus 3 minus 10 plus 4x squared, 4x cubed.
Okay, so we said that the standard form, we said if it's good for one thing, or there's one thing that it's good for. Well, no, there's more than one thing, but one of the things that it's good for we've already talked about. How, by looking at the standard form, we can basically immediately know what about the graph? The y-intercept. The y-intercept is the same as the constant term. Okay, the other thing here has to do with what's called the end behavior. The end behavior of a function is what happens as x gets very, very large, and what happens as x gets very, very large negative. Okay? So end behavior has to do with, here's the notation for that. This means let x get very large positive, or x go to infinity. And then very large negative. So this is what the reason we call it end behavior is because when x is very large positive, that's way out the right end of the graph, the right end, right? And when x gets very, very large negative, that's way out on the left end of the graph. So end behavior is talking about the left and right ends of the graph. So let's take a look at this here. If x was 1,000,000, that's a pretty big positive number, right? If x was 1,000,000, how would this term compare to this term? So x is 1,000,000, and this says do what? Multiply it together 3 times, 1,000,000. This says multiply 1,000,000 together 2 times. How would these two terms, how can you compare these two terms if x is 1,000,000? Pretty similar, about the same? Or different?
X is 1,000,000.
X is 1,000,000. What do we do to 1,000,000 in the leading term?
Raise it to the third power.
What does that mean, raise it to the third power?
Multiply together 3
Multiply it together 3 times. What about 39x squared? The next largest term. What are we going to do to the million?
Just
Multiply it
twice.
twice. Are these going to be close or far apart? How many times bigger will the 4x cubed be than the 3x squared? How many times bigger? 1 million times bigger, because we're going to multiply by 1 million one more time. Okay, now make x a trillion. How much bigger will the 4x cubed be than the 39x squared when x is a trillion? Trillion times bigger. So what happens as x gets very, very large? What really takes center stage? What takes center stage as x gets really, really large? The constant term? No, what takes center stage? The what? The leading term. Because the leading term will always be at least a trillion times greater than the other terms. Do you see? These become virtually 0 when x gets very, very large. Same thing with negative infinity. If you put in negative a trillion, this is still, in magnitude, it's still a trillion times bigger than this. Okay? And the trillion, I mean, compared to infinity, a trillion is a small number, right? We take a trillion to the trillion. That's starting to get bigger, okay? So the point is that for very large numbers, your leading term will always be much, much greater than the rest, to the point where these just disappear. They're like 0. So we can analyze the end behavior by just looking at the leading term. Does it make sense? So what will happen as x goes to positive infinity to positive 4x squared, 4x cubed? Will that be a large positive number or a large negative number? Large positive. And what will happen to 4x cubed when x becomes a very, very large negative number? Y will go to? Will it be a large negative or a large positive? It'll be a large negative because it's cubed. Because we're going to multiply it together an odd number of times, a large negative, we're going to end up with a large negative. So this is the idea of the end behavior of this graph, that as we go way out in positive x territory, what will the graph do? It's going to, as we go to positive infinity, y will also go to positive infinity. As we go to negative infinity, it's going to go negative. So this doesn't tell us anything about what's happening in the middle of the graph, just at the end. So that's why I'm just kind of drawing this piece out here, because it's only telling us for large values of x what y will do, and for very large negative values of x what y will do.
That's all just by looking at the leading term.
Just the leading term, because for those large values we know that leading term is at least 1 million, a trillion, a billion times larger than the next biggest term. And so those become virtually 0 compared to that. Okay, so the standard form gives us the y-intercept, we know that's 0, and it gives us the end behavior. What did the factored form help us with? Yeah, so if we know the end behavior, what do we have left to find? The middle behavior. In the middle of the graph. And we have a root at 0, we have a root at 4.25 and 5.5. So we can kind of start, now we have enough to kind of start connecting the dots here. Now we've already seen the graph, but pretending that we hadn't seen the graph yet, it's gonna go from here up to positive infinity. It's gonna go through and come back around, go up, come back down, and then go to negative infinity. So the last version was much prettier, but the point is, how do we figure out pieces of the graph from the different forms? Standard form gives us the y-intercept. It also helps us with end behavior. What's happening way out for large values of x to the right, large negative values to the left. Factored form is what we call the middle behavior. It's going to be the roots And the last thing we haven't talked about yet is the root behavior, but we'll save that for Monday. That doesn't mean we're done. We're going to practice one problem, but we'll save this thing called root behavior for Monday. So just hold on for that. So let's see if there's a good practice problem here.
So if your leading term is a negative number, is that going to change your end value?
Yeah, so this isn't the only, we have, yeah, you have to analyze for end behavior, you have to analyze each one separately. It won't always be positive y to the right and negative y to the left. Okay, it depends on what that leading term is. So for instance, let's have you look at on page 206. Look at, there's a function called k in the middle of the page. Do you see that? Yeah. Negative 6x, 3x plus 2 squared times x squared minus 4. So what I want you to do is find the roots, and then I'll go ahead and show you what the factor or the standard form is, and from the standard form you're going to find the Y-intercept and the end behavior. So you're going to find the roots, and you find the roots. Anybody have a root yet? Tell me one root.
0.
0 is one of them. What if it just said negative 6 and there was no x there? Would you have it? Would negative 6 be a root? No, that just would be that wouldn't be any root, because the roots are values of x that make the function 0. All right, so we got 6. Or I'm sorry, no, not 6. 0. Okay, another root. Negative 2/3. So does negative 2/3 makes this 0 right here? Okay. Negative 2/3. Okay. Now this is actually not fully factored.
Yeah. Another 2.
X squared minus 4. That continues to factor. How does that continue to factor? X plus 2, x minus 2, giving us the zeros. Negative and positive 2. Okay, so I'm starting the graph here by hand. I got those 4 zeros. Those come from the factored form. Okay, now, end behavior. So there's the standard form of this, what are we going to look at to figure out the end behavior? Which one? Negative 54 x to the 5th. As x gets very, very large, does y get very, very large positive or negative? Very, very large negative. Okay? As x gets very, very large negative, will that term get very large positive or negative? Positive. Okay, so now what's left is what's called the middle behavior, or what's the behavior around the roots, which we haven't talked about. We'll talk about Monday, but let me just graph just this much, and we'll see if this much is right. So you see that we got the roots right, and then it's hard to see because it looks vertical, but the graph is coming this way. From left to right, it's coming down through this root, okay? And from going right to left, the graph is heading up this way. It's just so steep you can't see. Okay, get started studying, and then you got homework Wednesday too. Yes, sir.